Optimization of yield lines in two-way slabs. This video deals with type 4 slabs. First, we will give the definition of the different types of slabs. First, you have a rectangular slab on all sides simply supported. That's type 1. On one side, it is clamped. Then it is type 2. When the two opposite longest sides of the slab is clamped, it's a type 3. Type 4, when two adjacent sides of the slab are fixed. Type 5, when 3 sides are fixed. And type 6 is when all sides are fixed. This video will handle the type 4 slabs. Using the yield line method, we know that the axis of rotations are the 4 support lines of the slab. And when the rotation axis is coming together, then you are crossing, then the yield line starts in the corner with an angle beta 1. We don't know yet the angle beta 1. We do that for the 4 corners, and then when the two yield lines cross, we connect them to have a yield line pattern that gives rise to a movable or to a mechanism, a possible mechanism. So all those parts of the slab can rotate around their rotation axis. Of course, when the slab is fixed, then we also have a yield line for the bending moment on top of the slab, and the same for this side. We assume that the maximum bending moment in the field is the same as the maximum bending moment at the top of the slab. When this is not the case, you just use, instead of M for this, you can use M1, which is a proportion of M, and then you can redo the calculations. But because we normally find it attractive to give the same reinforcement on top and bottom of the slab, so the assumption that M on the bottom is equal to M on the top is realistic. Then we have some geometric characteristics from S1 to S2, S3, and S4. And now we will express the different geometric characteristics in function of the angles beta 1 to beta 4. To have a two-way slab, you need the condition that B must be between A and 2 times A. And geometric restriction is, of course, that S1 plus S3 must be smaller than B. And S2 and S4 are together A. We will use the cotanger's rule, which says that the height of the triangle S1 is equal to the base, which is A, divided by the sum of the cotangents of the adjacent corners. But we know that the cotangents of, for instance, 90 degrees minus beta, this is equal to the tangents of beta. So we can write that S1 is A divided by the tangents of beta 1 plus the tangents of beta 4. For S2, when S2 is here, then you see easily that S2 is equal to S1 times the tangents of beta 4. Now we do the same for the other portions, the same ruling, and when we obtain those relationships. Now, to obtain a realistic yield line pattern, there are some conditions to it, because this point here cannot be situated somewhere there, because this yield line here could be horizontal, because it should be somewhere between the rotation of axis in the north and the rotation of axis in the south. They are parallel to each other. So Sx is then equal to S1 tangents beta 1, and on the other side, Sy is S3 times tangents of beta 1. This should be equal, so Sx is equal to Sy, and then we can do the same on the south side for Sv and Sw, gives you another relationship. And then we find that there is a relationship between the four angles. And we can now write one parameter in function of the other. So instead of 4 unknowns, you only have 3 unknowns. It doesn't matter. You can use beta 3 or beta 1 or beta 4. It doesn't matter. But you must obey this relationship to obtain a physical possible of a realistic yield line pattern. Now, because of symmetry, when you look at this, is a little bit more difficult, but there is a symmetry in it. And this symmetry means that when this leg and this leg is of the same kind, for instance, it's both are clamped or both are simply supported, then we know that beta 2 should be equal to beta 4 because the length of the legs forming this corner are the same. So it means that the influence should be the same. So beta 2 is equal to beta 4. Then we know with the tangents rule, this relationship, we now can write this as one in function of the unknowns, y1 and y4, which are the tangents of the angles beta 1 and beta 4. We do it so for S2, S3, and S4. So that's the most general expression of the geometric characteristics S1 to S4 in function of beta 1 to beta 4. This must be fulfilled, this condition, but S1 plus S3 smaller than B means that if you substitute S1 and S3 and you use beta over or B over A equal to alpha, then you know that Y1 to until Y4 must obtain this condition. Otherwise, the formulas are not valid. Beta, all angles are, of course, smaller than 90 degrees and positive. And the parameters we are working with is always the tangents of the angle. Now, we can summarize what we have found up till so far. Y4 is equal to Y2, or beta 2 is equal to beta 4. The Y is always the tangents of the angles. We have the definitions or the properties, the geometrical properties expressed in the angle properties. Now we can calculate the work done by the external forces divided by the load, the external load, divided by the unity of displacement. We look at this portion of the slab, which is existing of 4 triangles. So total load is S1 times A, and the mean deflection is then delta over 3. The same for the other side, which is A multiplied by S3 divided by 3. So now we got this explained. What's left is a summation of rectangulars with a side equal to B minus S1 minus S3 and then multiplied by A, and the mean deflection is delta over 2. We fill in the different variables and we obtain this expression. Now we calculate the work done by the internal forces divided by the bending moment and the unity of displacement. We project the bending moment m to the axis of rotation. So we got b, the length of the axis, divided by the angle of rotation, which is delta over S4. So we have b over S4. On the right-hand side, we have this bending moment projected to the axis of rotation, which gives you A divided by S3. On the bottom, we got B divided by S2. And on the left-hand side, we got M divided by S1. And then for the clamped side, on top of the slab, we still got this bending, this yield line. So it is B divided by S4. And on the right-hand side, A divided by S3. We substitute the different variables and we obtain this equation. We know that E must be equal to D. So M is now a function of alpha, which is B over A, and y1 and y2. So we need now to maximize the bending moment in alpha and in beta 1 and beta 2. And this is the function, and we can do that to take the partial derivative from the function to the parameter y1, put it equal to 0, and we solve it to obtain the optimum or y1 max or y1 extreme, which is the square root of y2. So we can write this formula optimized in the beta 1 angle, and we have a function which is a function of alpha and y2, and this is the expression. In the second step, we take the derivative to y2 and we put it equal to 0. We solve this equation for y2, and this is the formula for y2. Then we substitute y1 and y2 in the general formula to obtain the maximum bending moment as a function of alpha, which gives you this formula. Now let's look at the rectangular slab where B is 8.1 meters, A is 4.5 meters, and it's loaded with 20 kilonewton per square meter. The full green lines is the 30, 45, 60 rule. So it means this is 60 degrees, this is 60 degrees, this here is 30 degrees, and this is 45 degrees. We know for having a realistic yield line pattern, we must comply with this equation. The formula for the maximum bending moment was given in the previous slide. And we can apply this formula by using B over A, 8.1 divided by 4.5 is 1.8, and we have 18.5 kilonewton meter per meter. The beta 1, or the tangents of beta 1, we know that this is done by beta 1 optimum. It's the square root of y2, and this is equal to this formula, and you got the tangents is 1.119, which means 48.2 degrees. So instead of 60 degrees, you have got now 48.2 degrees in the optimized yield, in the optimized yield lines. We calculate now the beta 2, which is 38.4 degrees. Beta 3, we also calculate beta 3, which is 29.2 degrees, and then we calculate beta 4, which is of course the same as beta 2. So the dotted line is the optimization, and you see that the four corners have those values. Then we check if this is a realistic yield line pattern, and you see if you fill in the different values that we obtained here, then this equation is okay. The maximum bending moment with the 30, 45, 60 rule is then equal to the general formula of the bending moment with alpha and the tangents of 60 degrees, which is square root of 3, and the tangents of 45 degrees is 1. So now we know the variables y1 to y4. We substitute it in this equation to obtain the M30, 45, 60 formula of maximum bending moment. The optimized formula for maximum bending moment is then equal to this formula, like we've seen in previous graph. And now we can make a graph. On the y-axis is the ratio of the 30, 45, 60 degree rule divided by the optimized bending moment in function of alpha within its limits 1 and 2. We see now that the maximum difference is 3%. Let's take an example of a square slab with a dimension of 5 meters loaded with 20 kilonewtons per square meter. The full green lines are the yield lines with the 30, 45, 60 rule. The dotted lines are the optimized yield lines. So alpha is 1. We calculate the maximum bending moment according to the 30, 45, 60 rule. We find 14.2 kilonewton meter per meter. We calculate the optimized bending moment, it's 14.3. We divide both to obtain the ratio of 0.99. The angle of beta 2, it's 45 degrees. It's the same as with the optimized, as with the 30, 45, 60% rule. And beta 1, top, it's something less than 60 degrees. It's 55 degrees. You see that the difference between optimization or not is very small, and you can easily see it that the total length of yield lines are very small in variation. Let's look now to the other extreme when alpha is 2. So you have again a slab loaded with 20 kilonewton per square meter with a size of 5 and 10 meters, and alpha is then B over A, which is 2. The maximum bending moment obtained with the 30, 45, 60 degree rule. This is the green full line, the yield lines indicated by the green full line. This gives me as 23.6 kilonewton meter per meter. The optimized bending moment, which is shown here by the dotted line, is 24.3 kilonewton meter per meter, and the ratio between the two is 0.97. The optimized angle is 47 degrees instead of the 60 degrees with the 30, 45, 60 rule. And on the other side, instead of 45 degrees, we got 37.5 degrees. And the third angle, of course, is the same as beta 2. So beta 4 and beta 2 are the same. And beta 3 is 28 degrees instead of 30, because this angle is 60 and this is 30. We can now also look at it with another point of view. The maximum bending moment in function of alpha is equal to QH squared divided by a coefficient k. I call it k max in function of alpha. By filling in or by calculating k max in function of the formula of m max of the previous slides, we obtain this expression. And you see that this expression is only a function of alpha. So it's only a function of the geometric characteristics, which can be handy. On this graph, you will see on the x-axis the range from alpha from 1 to 2, and on the y-axis it is the k factor. Let's look at an example. We have a slab with a dimension of 5 by 7.5 meters, which means that alpha is 1.5. It's B over A, loaded with 20 kilonewton per square meter. So for alpha equal to 1.5, we obtain a K max factor of 24.7. Using this formula, you find 24.726 and so on. So we use 24.7, and the bending moment, maximum bending moment, is then 20, the total load, times the size A squared divided by the K max factor, which is 24.7. It gives you 20.24 kilonewton meter per meter. Beta 2 in this corner is 40 degrees. If the dotted line, it's 40 degrees. For the 30, 45, 60 rule, it's 45 degrees. And beta 1 is 50 degrees instead of 60. Beta 3, here it's 31 degrees instead of 30. You see it's always the same.